Time itself moves in one direction, and everything within it, every atom, every star, every whisper of energy, follows an invisible current we cannot reverse. We stand here, conscious observers, on a spinning rock, watching galaxies drift away from us at incomprehensible speeds, watching the universe expand into something stranger and emptier with each passing moment. Where is it all going? What awaits at the end of this cosmic journey? These questions have haunted humanity since we first looked up at the night sky and wondered if the darkness would one day swallow everything we know. The universe is not static. It has never been. From the moment of its violent birth, it has been in motion, expanding, cooling, evolving. But unlike the cycles we see on Earth, the seasons that return, the sun that rises again, the universe appears to be moving toward something final, something that will not reverse or repeat. We exist in what may be the universe's prime years, a brief window of cosmic time when stars still burn, when galaxies still collide and create new suns, when the conditions for life like ours can exist. But this window is closing. To understand where everything is going, we must first understand where it has been. Roughly 13.8 billion years ago, everything that exists, all matter, all energy, all space itself, erupted from an infinitely dense point in an event we call the Big Bang. In that first fraction of a second, the universe expanded faster than we can properly imagine, cooling from temperatures beyond comprehension to merely billions of degrees. Within minutes, the first atomic nuclei formed. Within hundreds of thousands of years, atoms themselves became stable enough to exist without being torn apart by radiation. And then came darkness. For hundreds of millions of years, the universe was truly dark. No stars existed yet. No galaxies. Just vast clouds of hydrogen and helium drifting through expanding space, cooling, condensing under their own gravity. But gravity, patient and inexorable, was at work. These clouds began to collapse, compressing until their centers became hot enough to ignite the first nuclear fusion reactions. The first stars blazed to life, massive and short-lived, burning through their fuel in cosmic eye blinks. When they died, they scattered heavier elements, carbon, oxygen, iron, into space, seeding the universe with the ingredients for planets, for life, for us. These early generations of stars clustered together, drawn by gravity into the first galaxies. And those galaxies, in turn, were drawn together into larger structures, galaxy clusters, superclusters, filaments stretching across hundreds of millions of light years. If you could step back far enough to see the entire observable universe at once, you would see a cosmic web, a network of matter, separated by vast voids of empty space. This structure, this web, represents the largest scale organization of matter in the universe. And it is all moving. In the early 20th century, astronomers began to notice something peculiar. When they examined the light from distant galaxies, they found that it was shifted toward the red end of the spectrum, redshifted, they called it. This redshift was a Doppler effect, the same phenomenon that makes an ambulance siren drop in pitch as it speeds away from you. The galaxies were moving away from us. More remarkably, the farther away a galaxy was, the faster it appeared to be receding. This was not because we were at the center of some cosmic explosion, but because space itself was expanding, carrying galaxies along with it like raisins in rising bread dough. This discovery fundamentally changed our understanding of the universe's fate. If the universe was expanding now, it must have been smaller in the past. Extrapolate backward far enough, and you arrive at that moment of origin, that Big Bang. But what does it mean for the future? If the expansion continues, where does it lead? For decades, Physicists assumed that gravity would eventually slow and perhaps reverse the expansion. Just as a ball thrown into the air must eventually fall back down, the mutual gravitational attraction of all matter in the universe should slow the expansion, perhaps even cause a contraction, a big crunch that would return everything to a point, possibly to bounce back in a new Big Bang, a cosmic cycle repeating forever. It was an appealing idea, a kind of cosmic immortality, a universe that could never truly end. But the universe had other plans. In the late 1990s, two independent teams of astronomers were measuring distances to very distant supernovae, exploding stars that serve as cosmic distance markers. What they found defied expectations. The distant supernovae were farther away than they should have been if the expansion was slowing down. The expansion wasn't slowing at all, it was accelerating. Galaxies were flying apart faster and faster, as if some invisible force was pushing them. This discovery earned its discoverers the Nobel Prize and plunged cosmology into a crisis. What could possibly be causing this acceleration? The answer, frustratingly, is that we don't really know. We call it dark energy, a placeholder name for our ignorance, a label for the 70% of the universe's total energy that we cannot see, cannot touch, cannot understand. We know it's there because we can measure its effect, the accelerating expansion, but we have no idea what it is. It might be a property of space itself, a kind of intrinsic energy that comes with every cubic meter of vacuum. It might be a new field pervading all of space. It might be evidence that our understanding of gravity on cosmic scales is fundamentally wrong. But whatever dark energy is, it dominates the universe's future. And that future is cold and dark and lonely. Let us project forward. Right now, we live in what is sometimes called the stelliferous era, the age of stars. Stars are being born in galaxies across the universe. Our own Milky Way creates roughly one new star per year. These stars will live for millions, billions, even trillions of years depending on their mass, pouring light and heat into space, creating the conditions for planets, for chemistry, for life. But star formation requires raw material gas and dust, and that supply is finite and dwindling. As the universe expands, galaxies are being carried away from each other. The ones that are not gravitationally bound together in clusters are receding at ever-increasing speeds. Eventually, they will be moving away faster than light can travel. Not because they are moving through space faster than light, which is impossible, but because the space between them is expanding so rapidly. Light from these distant galaxies will become so redshifted that it fades away entirely. One by one, distant galaxies will disappear from view, not because they have died, but because their light can no longer reach us across the expanding gulf of space. In 100 billion years, perhaps 200 billion, the night sky will look very different. All the galaxies beyond our local group, the Milky Way, Andromeda, and a few dozen smaller companions, will have vanished beyond the cosmic horizon. A civilization arising in that distant future would look out at the cosmos and see only their own galaxy floating alone in an infinite darkness. They would have no evidence of the Big Bang, no visible expansion, no way to deduce the universe's history. The cosmos would appear static and eternal, a single island of stars in an endless void. All the evidence we have painstakingly gathered about the universe's origins would be gone, erased by expansion. But even within our local group, change is coming. The Milky Way and Andromeda are gravitationally bound, falling toward each other at hundreds of kilometers per second. In about 4 billion years, they will collide. This will not be a violent crash of stars. Smashing into each other. Space is so vast that actual stellar collisions will be rare. Instead, the two galaxies will pass through each other, their mutual gravity distorting both into long, tidal streamers of stars. They will swing apart, then fall back together again and again, eventually settling into a single merged elliptical galaxy that astronomers have playfully dubbed Milkomeda. Around the same time, our Sun will be dying. It is middle-aged now, about 4.6 billion years old, fusing hydrogen into helium in its core. But in another 5 billion years, the hydrogen fuel will run low. The core will contract and heat up, causing the outer layers to expand. The Sun will become a red giant, swelling until it engulfs the inner planets, Mercury, Venus, and possibly Earth. Our world, if it survives at all, will be a scorched, lifeless cinder, orbiting a bloated, dying star. Eventually, the Sun will shed its outer layers entirely, creating a beautiful planetary nebula, while its core collapses into a white dwarf, a dense, hot ember slowly cooling in the darkness. This is the fate awaiting all stars like the Sun. The massive stars, those dozens of times the Sun's mass, will die more spectacularly in supernova explosions, some leaving behind neutron stars or black holes. But all stars, regardless of their mass, will eventually exhaust their fuel. And as the universe expands and cools, the raw material for new stars, the hydrogen and helium gas, will become increasingly dispersed, unable to collapse and ignite. Star formation will slow, then sputter, then cease entirely. In about 100 trillion years, the last star will be born. In about 120 trillion years, that last star will die. The stelliferous era, the age of starlight, will be over. The universe will enter what is called the degenerate era, dominated not by burning stars, but by stellar remnants. White dwarfs, neutron stars, black holes, and cold brown dwarfs that never quite ignited. These objects will drift through galaxies that are themselves just gravitationally bound collections of dead stars, invisible except for the faint infrared glow of cooling white dwarfs. But even this era will not last forever. White dwarfs will cool over trillions upon trillions of years, eventually becoming black dwarfs, cold, dark spheres of crystallized carbon and oxygen, emitting no light at all. Protons themselves, the building blocks of atomic nuclei, may eventually decay, dissolving matter into radiation. The timeline for this is speculative if protons decay. They do so with a half-life of at least 10 to the 34 years, far longer than the current age of the universe. But given enough time, even the most stable matter may disintegrate. As matter decays or falls into black holes, the universe will enter the black hole era. Black holes, those regions of space-time where gravity is so strong that nothing can escape, will be among the last surviving objects. They will grow by occasionally swallowing whatever matter drifts too close, merging with other black holes when their wanderings bring them together. But black holes are not eternal. Stephen Hawking demonstrated that they emit radiation due to quantum effects near their event horizons. This Hawking radiation is incredibly faint. A black hole the mass of the Sun would take 10 to the 67 years to evaporate. Supermassive black holes, millions or billions of times the Sun's mass, will last even longer, 10 to the 100 years or more. But eventually, even they will evaporate. The last black hole will emit its final photon of radiation and vanish, leaving behind nothing but empty space. And then comes the dark era, the final epoch of the universe. Space will contain nothing but a thin, cold soup of photons and fundamental particles, spreading ever farther apart as the expansion continues. The temperature of the universe will be unimaginably close to absolute zero. No stars will shine, No planets will orbit. No structures will exist. Just individual particles, alone, separated by distances so vast that they will never encounter another particle for the remainder of time. If dark energy continues to behave as it appears to now, the expansion will accelerate without limit. Eventually, even atoms themselves might be torn apart in what is called the Big Rip, as the expansion of space overwhelms even the electromagnetic forces holding electrons to nuclei. But current evidence suggests this is unlikely. More probably, the universe will simply expand and cool forever, asymptotically approaching but never quite reaching absolute zero, a state of maximum entropy where no gradients exist, no energy can flow, no processes can occur. This is heat death, the ultimate fate predicted by thermodynamics for any closed system, now applied to the entire universe. It is a bleak picture, almost unbearably so. Everything we are, everything we have built, every thought, every work of art, every moment of love or joy or sorrow will not just be forgotten, there will be no one left to do the forgetting. The universe itself will become a void, empty and cold, where nothing happens and nothing ever will. But we are not there yet. We are here now in the most remarkable period of cosmic history. We exist during the stelliferous era, when stars still burn, when galaxies collide and create new suns, when the universe is rich with energy and structure and possibility. We are made of atoms forged in the cores of dying stars, scattered across space in supernovae, gathered by gravity into planets where chemistry could become biology, where life could emerge and evolve and eventually produce consciousness, capable of contemplating its own origins and fate. This is not a small thing. The fact that the universe can produce beings capable of understanding it is extraordinary. We are a way for the cosmos to know itself, as Carl Sagan put it. And even though our existence is temporary, even though the universe will eventually fade into darkness, the fact that we existed at all matters. The thoughts we think, the connections we make, the beauty we create and perceive, these have value not because they are permanent, but because they are real. Understanding where the universe is going also helps us understand how we got here. The Big Bang was not just an explosion of matter, but an explosion of possibilities. In that first fraction of a second, the fundamental forces separated, the laws of physics took their current form, and the initial conditions were set that would determine everything that followed. Tiny quantum fluctuations in the density of the early universe were stretched by inflation into the seeds of galaxies. Regions that were slightly denser than average attracted more matter through gravity, forming the first stars, the first galaxies, the cosmic web we see today. But why those particular fluctuations? Why those specific laws of physics? Why did the universe begin in a state of extremely low entropy, far from equilibrium, allowing for the complex structures and processes that make life possible? These are questions that science is still grappling with. Some physicists propose that our universe is just one of many in a vast multiverse, each with different laws and constants, and we find ourselves in this particular one simply because its properties allow for our existence. Others suggest that we are missing some deeper understanding of why the universe is the way it is. The cosmic microwave background, the faint afterglow of the Big Bang, visible in all directions, provides a snapshot of the universe when it was just 380,000 years old. Encoded in the tiny temperature variations of this radiation is information about the universe's composition, its age, its geometry, and its fate. By measuring this radiation with increasing precision, we have learned that the universe is flat, or very nearly so, meaning parallel lines will never converge or diverge as they would in a curved space. We have learned that ordinary matter, the stuff of stars and planets and people, makes up only about 5% of the universe's total energy. About 27% is dark matter, invisible stuff that we know exists because of its gravitational effects on galaxies and galaxy clusters. And the remaining 68% is dark energy, driving the accelerating expansion. These numbers are strange. Why these proportions? Why is dark energy just strong enough to cause acceleration, but not so strong that it prevented galaxies from forming in the first place? If dark energy were significantly larger, the universe would have expanded so rapidly that matter never clumped together to form stars. If it were zero, the universe might have recollapsed long ago. We happen to live in a universe balanced between these extremes, during an era when both stars and life can exist. Is this coincidence, design, selection effect in a multiverse? We do not know. What we do know is that our position in time is special. We live in a window of cosmic time that spans perhaps a few 100 billion years, from the formation of the first stars to the death of the last, out of a cosmic future that may extend for 10 to the 100 years or more. We are temporally located very near the beginning of the universe's story if we measure by the logarithmic scale of deep time. Almost the entire future of the universe lies ahead. A future that will be dark and cold and empty, but a future nonetheless. This raises profound philosophical questions. If the universe ends in heat death, does anything we do matter? If all structure and complexity will eventually dissolve into a featureless void, what is the point of existence? These questions have troubled thinkers for as long as we have understood the universe's trajectory toward entropy and disorder. One response is to reject the premise. Just because something is temporary does not mean it lacks meaning or value. A song is temporary, ending in silence, but we do not consider music pointless. A flower blooms and withers, but its beauty is real while it lasts. We are processes, not objects, patterns of matter and energy that temporarily cohere into forms capable of experience and thought. The fact that these patterns will eventually dissipate does not negate their present reality. Another response is to embrace uncertainty. Our understanding of physics is incomplete. We do not know what dark energy is, or whether its strength will remain constant. We do not know whether protons truly decay, or what lies beyond the standard model of particle physics. It is conceivable, though perhaps unlikely, that the universe could surprise us, that new physics at extreme timescales could allow for structures or processes we cannot currently imagine. Some speculative theories suggest that fluctuations in the far future could spontaneously create pockets of low entropy, brief islands of order, in an ocean of disorder. Others propose that consciousness itself might be preserved or reconstituted through mechanisms we do not yet understand. But even without such speculations, there is value in confronting the universe as it appears to be. There is a certain austere beauty in the ultimate simplicity toward which the cosmos tends. The universe began in a state of perfect symmetry, all forces unified, all of space-time smooth and featureless, and it will end in a state of perfect equilibrium. In between, there is us, and stars, and galaxies, and the brief flowering of complexity that we call the history of the universe. This is where everything is going. Outward, into darkness, into cold, into silence. The galaxies will disappear beyond the horizon of observation. The stars will gutter and die. The black holes will evaporate, and space itself will expand forever, carrying the last scattered particles farther and farther apart, until each is utterly alone, beyond the reach of any other, in a darkness that will never end. We are watching it happen in real time, or at least in the slow motion, of cosmic time. Every second, space expands a little more. Every year, distant galaxies are a little farther away, their light a little more redshifted. The universe is approximately 13.8 billion years old, but it has been accelerating for only about the last 6 billion years. Before that, the mutual gravity of matter was strong enough to slow the expansion. But as the universe grew larger and matter became more diffuse, gravity's influence weakened while dark energies remained constant. Eventually, dark energy won and the acceleration began. This acceleration means that there is a cosmic event horizon, a boundary beyond which light emitted today will never reach us, even if we wait forever. Objects beyond this horizon are causally disconnected from us. Nothing they do can ever affect us, and nothing we do can ever affect them. As the universe expands, this horizon encompasses fewer and fewer galaxies. The observable universe, paradoxically, is shrinking in terms of the number of galaxies it contains, even as the space within it expands. For civilizations in the far future, assuming any exist, this will have profound consequences. All evidence of the wider universe will fade. The cosmic microwave background will be so redshifted that it becomes undetectable. The elemental abundances left over from the Big Bang will have been processed by stars into heavier elements, erasing another line of evidence. Future cosmologists will look out at a seemingly static universe, one galaxy alone in darkness, and they will have no way to discover the truth of the Big Bang, the expansion, or the existence of other galaxies. They will be missing crucial pieces of the puzzle simply because their temporal location is different from ours. This is a humbling thought. It suggests that our own understanding of the universe might be similarly limited by our temporal and spatial position. There may be aspects of reality that are simply not accessible to us, not because we lack the technology or intelligence, but because the information has already been erased by the passage of time, or is beyond our cosmic horizon. We are cosmically provincial, our knowledge bounded by the edges of observation, and yet we have learned so much. From ancient myths about creation to the precision measurements of modern cosmology, humanity has pieced together a coherent story of the universe's past, present, and future. We understand the nuclear fusion that powers stars, the gravitational dynamics that shape galaxies, the quantum mechanics underlying matter itself. We have traced the universe back to fractions of a second after the Big Bang, and forward to its ultimate fate trillions upon trillions of years hence. This is one of the great intellectual achievements of our species. It is also a reminder of how young we are. Our species, Homo sapiens, has existed for perhaps 300,000 years. Civilization is only about 10,000 years old. Modern science is less than 500 years old. Cosmology, as a rigorous, quantitative discipline, is barely a century old. And yet, in this brief span, we have learned where we came from and where we are going. We have learned that we are stardust, that every atom in our bodies was forged in the nuclear furnaces of stars or in the violent explosions that mark their deaths. We have learned that the universe is vast, almost beyond comprehension, containing hundreds of billions of galaxies, each with hundreds of billions of stars. And we have learned that this vast cosmos is moving toward an end, an ultimate dissolution into cold and darkness. What should we do with this knowledge? How should we live, knowing that everything is temporary, that the universe itself will die? These are not scientific questions, but existential ones, questions each person must answer for themselves. But the science itself can inform those answers. Understanding the scale and age of the universe puts our own lives in perspective. Our individual lifespans are infinitesimal compared to the age of the cosmos, yet they are all we have. The time we are given, however brief, is precious precisely because it is finite. The universe may be heading toward heat death, but we are heading toward our own personal heat deaths much sooner, on timescales that matter to us years, decades, perhaps a century. The universe is stable and predictable. The sun will rise tomorrow. The stars will shine tonight. We have time, not infinite time, but enough time to live fully, to love, to learn, to create meaning in the face of an uncaring cosmos. And perhaps that is the ultimate answer to the question of meaning in a dying universe. Meaning is not something we find in the cosmos itself, but something we create through our choices and actions and relationships. The universe does not care about us. It is vast and indifferent, operating according to laws that have nothing to do with human values or desires. But we care about each other. We care about beauty and truth and justice. We create art and music and literature. We explore and discover and build. We love and grieve and hope. These things matter because we are here to make them matter. The universe is going toward darkness, but it is not there yet. We are alive in the age of starlight, and that is a gift beyond measure.